Welcome to BC Gnomonics. In this video, we're going to be taking a look at the demonstrational Armillary Sphere, a device capable of modeling and tracing the path of the Sun and celestial sphere for any given day of the year at any latitude. The sphere is able to accomplish this by modeling to scale all the key features of the celestial sphere. Before we go over the modeling mechanics, let's go over each of these key elements and what they represent in terms of the Earth and celestial sphere. So, starting up at the center, we have a model of the Earth itself, and rotating around it are the three key circles of this device: the equator, the Tropic of Cancer, and the Tropic of Capricorn. The Tropic of Cancer models the path of the Sun at the summer solstice, the equator, its path at the equinoxes, and the Tropic of Capricorn, its path at the winter solstice. Slightly less important to the demonstrational purposes of this device, we have the equinoctial color as well as the solstitial color. Arcing over the entirety of the sphere, we have the local meridian, and perpendicular to that, we have the local horizon, which we'll get into in a minute. Now, to model the Sun for any given day of the year, the sphere is inclined to the degree of your latitude. A point on the ecliptic is marked, and the entirety of the sphere is rotated with that point kept in mind. It's this rotation that allows the path of the Sun to be traced out. Now, you'll likely have noticed that I've already marked a point on the ecliptic, this being the beginning of Virgo, or today's date. Now, just making sure we have 45 degrees roughly of inclination, that is my current latitude. We're ready to model the Sun. So, starting out on the horizon, we have the Sun rising in a bit of a position slightly north of east, which makes sense considering at the summer solstice, the Sun rises at its farthest northern point, and at the equinoxes, it rises due east. The current position is right about in the middle of the summer solstice and equinox, approaching the equinox, so it's just a bit north of east. Now, starting off at that location, we rotate the sphere, and the arc of the Sun for that day can be traced out. At noon, the moment when it crosses the local meridian, we can see how high the Sun will arc for this given day. It's not quite as high as the arc of the summer solstice, but it's higher than the mark of the equinox. Again, this makes sense considering it is between those two dates. As we continue to rotate the sphere, we see the Sun fall beneath the western horizon, again at a northwestern position. Now keep in mind that this can be modeled for any latitude for any day of the year. So if we wanted to model the North Pole at the summer solstice, we would mark this position on the celestial sphere and trace it in a circle around until it makes a full circuit. That's a complete day. Now, as you may have noticed, the Sun does not set on this day. That is because with the circle of the summer solstice parallel to the equator, and the North Pole being 90 degrees above the equator, there is no opportunity for the Tropic of Cancer to dip below the local horizon. Likewise, at the winter solstice of that very same location, we can trace out a line, and here we can see that the Sun will never rise. At the other extreme, we have the equator, And here we can see that the arc above the horizon is almost 90 degrees. It's not actually 90 degrees just because the model here is constrained a bit. This is roughly 10 degrees above the equator, so it's not truly 0 degrees. If it were 0 degrees, though, we would see that at the equinoxes, the sun's arc would be 90 degrees and pass directly through the zenith, the only day and place on Earth where this is possible. But for our purposes, again, let's just return one more time to the 45-degree mark. For any given day of the year, we can trace out the path of the sun. And one of the key features of this is being able to see the differences in the culmination of the sun. So as I said before, we can see the culmination here is in between that of the equinox and the solstice. At the winter solstice, it's much lower, only reaching that high in the celestial sphere above the local horizon. Now, because this model is relatively limited, there aren't scales to measure exactly how high the sun's culmination is for any given day. Although on some models, you can actually measure that and tell exactly what degree in the sky the sun will reach on any given day. But that will conclude this demonstration, and I hope you enjoyed. One thing I will note is that when orienting this dial true north, or this armillary sphere true north, you get a very intuitive representation of the celestial sphere as it actually matches up perfectly with the true one. So you can watch this in a separate video, listed below this one if you'd like. But the modeling is even more intuitive when you have this dial, this armillary sphere oriented true north. So you can, for example, extrapolate outward the position of the rising sun to the actual position of the sun. Likewise, the position at noon, if you were to look upward in this direction, you would see the actual sun in the sky at this very point on the larger celestial sphere. So I hope you enjoyed watching, and I would suggest watching the outdoor demonstration video if you would like a more intuitive version of this demonstration.